Hello, am I audible, students? Kindly confirm if I'm audible.
Audible, sir.
Okay, fine. So let's start with the live session for the week 5 for the course Introduction to Semiconductor Devices, which is taught by Professor Naresh Kumar Imani from IIT Hyderabad, and I am Anant Singhal, a PhD student from IIT Jodhpur, and I'll be assisting you in solving similar assignment problems that are related to week 5 topics according to the course content, and that will help you in solving some of the problems that have been given to you in week 5 assignments. So, in the previous weeks, we have already covered the content till week 4. And as I said in the last week also, that the last week content was very important with respect to the further topics in the course. You must have been aware of now how to make band diagrams for different types of junction, such as PN junction, isotype junction, such as NN plus junction, and P plus junction, etc. And once you know that how the barrier is coming between the junctions and how we are making the band diagrams, then it is very easy to solve further problems. So as you can see in this week, we'll be talking about PN junction again. Give me a moment. Yeah. So in this week, again, we'll be talking about PN junction, but now we'll go away from the equilibrium conditions that we have discussed in the last week. In the last week, we have discussed the PN junction problems for zero applied bias, that is, we have not applied any voltage. So it was at electrical as well as at thermal equilibrium. But for this week, we'll be applying some of the voltages across the PN junction, and we'll be mainly talking about how the band bending happens under the applied bias, and we'll be talking about some of the ideal diode equations and the corresponding numericals according to the problems. So is there any particular doubt from the last week? Like, do you remember each and everything, how to make a band diagram, etc.? If you have any doubt, you can ask right now only, because that will be helpful for you in solving these problems that are related to week 5. So I hope you all already know how to make a band diagram for a PN junction and even for an isotype junction. If possible, we can start with some of the maybe one or two questions from the topic of previous week, that is some of isotype and PN junctions at equilibrium conditions, so that the concept will be revised and you will be able to solve this week's problems quite easily. So shall we cover some problems for equilibrium conditions again? You can quickly let me know by opening your mic or even in the chat box.
Yes, sir.
Okay, fine. So let's try to do some of the problems then. So let's do a very quick problem for a PN junction, which is again at equilibrium bias. That is, there is no voltage applied. So let's say I've taken a PN junction in which the acceptor ion concentration that I am taking is 10 raised to power 17 per centimeter cube, and the donor ion concentration that I am taking is, let's say, 5 into 10 raised to power 15 per centimeter cube. And temperature is again at room temperature 300 Kelvin. That will tell that the VT is nothing but 25 milli electron volts, and Ni am taking as, these are all the constant. I guess this is now very clear from the last lectures that how we have gone through this. So these are the dopings, etc. So first, the main point of doing this is, the first problem is you need to sketch the band diagram for this particular PN junction. Then the second problem is you need to determine the built-in potential, that is BBI. The third problem is maybe determine XP and XN, that is the depletion width on P side and the N side. And at last, you need to determine maybe the electric field. This is what we have already covered in the last week, all of these formulas and each of the nature of the plots that we'll be going through. So maybe you can take your time and let me know quickly. Maybe if someone already knows, you can open your mic and let me know the answers to this. So I'll repeat again. We are doing one or two problems for the equilibrium conditions, and then we'll be going for the applied bias. So this is the first problem that is similar to the previous week's problem. For a PN junction, you need to first sketch the band diagram. So you should write in your notebooks. I have given the doping, etc. for P side and N side, and I have given the intrinsic carrier concentration. And the further problems are numericals. So you need to determine the built-in potential, the depletion width on both P side and N side, and the electric field. So let me ask you some quick questions. So in this question, we know that Na is what is given is greater than Nd. So can anyone tell what will be greater, Xp or Xn?
It's N.
Yeah. So as she said that N will be greater because we have read in this last lecture that the product of Na times Xp is nothing but Nd times Xn. So the area of the charge density should be equal. That means that if we have a higher Na, then the Xp will be lower. That is, higher doping means a lesser depletion width on the either side. So a higher p-type doping means a lesser depletion width on the p side. So that is why we will have a higher Xn for this particular question as compared to the Xp. So that is great. So maybe I can do the first question, maybe sketch the band diagram uh, to maybe go ahead, and then you can let me know the numerical answers in the chat box. So as I have given a P N junction in which P I have given as 10 raised per 70, and N I have given as the doping as 5 into 10 raised per 15 per centimeter cube. So as she said that since we have a P type higher doping, we will have a higher depletion width over the P side, that is the acceptor ion Na ions, and we will have a higher depletion width on the N side, that is the donor ions. So this is how now we'll be making the band diagram. So this is again a reminder that this is at equilibrium. So at equilibrium, can anyone quickly tell how the Fermi level will be? A bit quicker. At equilibrium, can someone tell the Fermi level how it will be?
Middle of the junction.
Sorry?
Middle of the junction.
No, no.
1 and
They will
I'm
be
not
aligned.
asking the intrinsic, I'm asking about the Fermi level.
They will be aligned.
Yeah, so it will be aligned means it will be constant throughout the junctions. By aligned mean that we means that we have not applied any bias, so Fermi level will be constant for both P and N side. So let's say this is what I'm writing at EFN, and this will be EFP. So this will be aligned because there is no applied bias at equilibrium. And then we can go ahead with the same approach. So we know that this is P side and this is N side. So in this side, what we'll have is we'll have the P side. Give me a moment. Yeah. So for P side, the valence band, the Fermi level will be nearer to the valence band because, sorry, because it is a P type of semiconductor. And for the N side, what we'll have is we have the Fermi level near to the conduction band. This is, I hope, now everybody knows all these things. And this dotted line is corresponding to the EI, that is what is in the middle of both EC and EV. So is there any particular doubt in this band diagram? Because this is quite easy. I hope now you all can make band diagrams easily. Is it fine?
Yes, sir.
So this particular difference will be nothing but Q phi P, and this particular difference will be Q phi N as we discussed, and the VBI is nothing but the sum of phi P plus phi N. So this is VBI basically. So this will be the band diagram, and now coming to the VBI. So has someone calculated any answers for the VBI? This is quite straightforward now. Are you trying it or should I solve it by myself? Anyone? Okay, so let me give it a go then. So VBI is nothing but VT ln NA times Ni square, and we know all the values that are given in the question. So this is 0.026 ln Na is given as 10 is power 17, then this is 5 10 is power 50, and Ni square is 1.5 square is 2.25, and this is 20. So this will be around, I don't know, 0.026 ln. This is 32, this is 20. So this will be 5 divided by 2.25 into 10 is per 12. So has anyone got any answer?
0.71.
Yeah, so 0.7. Okay, what I
1.
am getting is 7.3. I'm not sure that. So you can check,
Okay.
maybe it will be around 0.7 volts only, that is for sure. So VBI for this question will come around 0.73 volts. Then we are going towards the next part, which is finding X and NXP. We all know, we have already seen that N is greater than ND in this question. So uh, Xn will be greater than XP. So let's calculate the Xn first. So I hope you already know the formula now. So this is 2 epsilon s VBI by Q. And for Xn we have Na by Nd, 1 by Na plus Nd. And for XP we have similarly 2 epsilon s VBI by Q, Nd by Na, and 1 by Na plus Nd. So I'm quickly trying to calculate Xn. You can also try to do it side by side and let me know the answers. Maybe in micrometers, that will be great. So Xn will be 2 times epsilon will be 8.85. So this will be 10 is per minus 14. So I'm writing each and everything in centimeters since question says each and everything in centimeter. Nd by Na will be 10 raised per, sorry, I'm calculating Xn. It will be Na by Nd and 1 by Na plus Nd. So it will be 10 is per 17 plus 5 into 10 is per 50. So if someone has got the answer, they can already let me know. Otherwise, I'll solve it. So this will be 10 is per 5, 10 is per 2. This will be 7. Taking 10 is per minus 5, maybe common will take. I left it to 11.7. PY is 0.73. On 1.0, 1.6 into 1.05, that will come out from this and multiply by 5. So this will come out in centimeters. So let me quickly calculate it. Um, 2 times 17 is, so this is what I'm getting, 4.26 times 10 raised by minus 5 centimeter. That will give me 0.426 micrometer. I hope you are all getting the similar answers. Similarly, you can calculate the XP also. That will be lesser. I guess I have the answers to that. So XP will come out, you can calculate at your home. So it will come out to be 0.02132 micrometer. and the total depletion width, we know it is nothing but xp plus xn. That will come around 0.447 micrometer. So you should calculate these all of these terms at home also, because that will help you in solving. uh, like it will help you practice for the problems in during the exams. You might need to solve all of this. The final question is the maximum electric field that is at, we all know that the maximum electric field for this band diagram is, if you remember, is at the x equals to 0, and we already have the formula, so this is E max. So we need to calculate this. So does anyone remember the formula for E max? Anyone?
square root of minus square root of 2q by epsilon v naught by 1 by na plus 1 by
Minus
nd
square root of 2q.
by epsilon
Hmm.
vbi divided by 1 by na plus 1 by nd.
Okay, so again, I guess you're guessing confused. This is a similar formula for the depletion width, not peak electric field. So peak electric field, if you remember that we calculated for both the sides, this is nothing but minus q n d x n by epsilon s, and that was equals to q n a x p by epsilon s. And from this, we got to know that n d x n should be equals to n a x p. So this is what the formula stands for, peak electric field. So we just need to calculate this only in this particular problem. So yeah, this is quite straightforward. So I'll just write the absolute values. I hope it is clear, right?
Yes.
Yeah. So I'm using the ND terms. So I'm using the XN. XN we calculated 0.426. So 10 is for 17 is not, no, 10 is for 17 is XP. So I'm using the XP then. So this will be 2.132 10 is for minus 6 centimeters. Then we have epsilon, which is, yeah. So this is what we have, and maybe you can solve it later. I'll let you know the answer. I have it. So this will come out to be something 32.94 kilovolt per centimeter. I hope these all things are now clear to all of you from the last lecture. I'm just revising one or two problems. Is it fine? Is there any
Sure.
doubt in this? Okay, fine. So now what you can do is we can do a isotype very quickly. So so you'd want to do it for a n-type isotype or a p-type. You can quickly let me know. You need to do maybe draw a band diagram only. I guess we already did for NN plus in the last lecture, or PP plus. I don't remember exactly. Does anyone remember?
So I think we did for nn plus.
Okay, NN plus. So we can try for PP plus junction, maybe P minus, let's say. So P is on the higher side, P minus on the lower side. Then what does it mean? So we have a P minus junction in which the Na for the P type, that is P, is given as 10 raised to 15 per centimeter cube, and Na for P minus is given as, okay, sorry. So let's say this is PP plus only. So P plus it is given as 10 raised to 17 per centimeter cube. Again, everything it has room temperature, so you can assume Vt as 26 milli electron volts. So you just need to calculate the magnitude of VBI. Yeah, the first part is again sketch the band diagram. You should always write in your notebooks side by side. And the second problem is magnitude of VBI. So even it will be better if anyone can explain how the band diagram will be made for this, and then we can go for the VBI. Anyone wants to explain this? Okay, fine. Maybe I'll try. Yeah. So let's try to do it. So let's first make the junctions differently. So this is a P type of semiconductor in which we have EI, EC, EV, and this is P plus, which is again this will be similar. And again, this problem is at equilibrium. So can anyone tell the Fermi level will be closer to the valence band for which case?
P plus.
Yeah. So I hope everyone understands this, that P plus, since we have a higher doping, so the Fermi level will be more closer here and it will be on the higher side here. This is what we already discussed in the last lecture, and the electrons always flow from higher Fermi potential to the lower Fermi potential. That is also we discussed. So what will happen? This P thing will go down to align the Fermi level. So maybe I can make the band diagram now. Yeah. So let's say the Fermi level is aligning like this. This is EF at P side and this is EF at P plus side. So let's say the Fermi level is here and it will be something like this. And then we have a EI, and similarly we have a EC. Sorry. I hope everybody understands this. So this is EI, this is EI. So this particular thing, which is this distance, this is nothing but Q phi P. This distance is nothing but Q phi P plus, and this is VBI, we all know. So VBI is nothing but, we discussed in the last lecture for NN plus, I guess. This is nothing but Q phi P plus minus Q phi P. And from this, if you remember, we got to know that the first term is VTLN NA, maybe NA 1 by NI minus VTLN NA 2 by NI. I'm assuming, yeah, NA1 is greater than NA2, which will give us the VBI of VTLN NA1 by NA2. We did for NN plus junction in the last lecture, which was ND1 by ND2. Similarly, we are getting for the P type as Na1 by Na2, and we already know each and everything. So I guess we can calculate this. So this is 0.026 ln. Yes, one was 10 this was 17 and one was 15. So it will come around 0.026 ln 100. Ln 100 is 4.3, 2.303. So 4.606 times 0.026. It will come out, let me calculate it quickly. It will come out to be 0.119756 volts. Is it clear to each and everyone? The isotype and the PN junction, how the band diagrams are getting made, and how we are calculating this barrier and electric field and all. Is there any doubt? Because now we'll move towards the applied bias, maybe reverse bias and forward bias PN junction. Shall we move ahead, or you have any doubts?
It's clear, sir.
Okay, fine. So let's first do the most important part. So let's first read about the reverse junction PN junction. Oh, sorry, reverse bias PN junction. Okay, so can anyone tell what is the difference between reverse and forward biased junctions? Can anyone tell what is forward bias and what is reverse bias?
In forward bias, an external electric field is applied in the direction um, opposite to the barrier.
Okay, that's one case. So let's say I have a PN junction. So in forward bias, because we know that the P side will have more holes and N times will have more electrons. So what we do is the positive voltage is applied on the P side, basically. The negative voltage is applied on the N side. So this is a forward bias P junction. Let's say this is VA. And similarly, in reverse bias, what we do is at N side we connect the positive potential, and at P side we connect the negative potential. This is a very basic understanding of what is forward and reverse bias. So basically, for forward bias, what I'm trying to say is Vp is greater than Vn, and for reverse bias, Vp is less than Vn. Let's say this is voltage at P point, this is voltage at N point. I hope it makes sense. So one thing it is very clear. So first we are talking about reverse bias. So in reverse bias, as I have already told you, so let's say this is a PN junction, this PN. So reverse bias means the P side is connected to the negative potential. So we are now applying some biases. So I'm representing this as VR, the voltage, reverse bias voltage. So please try to understand here. So what we have is we have a negative potential on the P side. So we have, let's say I'm writing negative here, and we have some positive potential on the N side. Is that clear till now? Any doubts here?
It's no, sir.
Okay. So since we are applying positive potential on the N side, so we know that the N side we have dominant holes. Oh, sorry, not holes, but electrons. So these electrons will get attracted towards this positive voltage, and we have holes on the P side, which will get attracted towards this negative voltage. So what it will do is, so let's say this was a case when I have not applied any bias. Maybe wait, yeah. So let's say this was a case where I have not applied any bias, and I have certain Na ions here and Nd ions here. So once I apply a certain negative voltage now from the external bias, so what it does it, we have more diffusion of the majority carriers, that is we have more holes getting attracted towards this side, and we have more electrons getting attracted towards this side. So what it will do it, I guess this is very obvious now, that it will create a larger depletion region as compared to the previous case. So now we will have a broader depletion width. Does it make sense? So earlier it was this, and due to the application of the voltage it has now become this. So let's say this is W new and this is W. So W new has become greater than W. Does it make sense to each and everyone?
It's a
Okay, yeah. So if this is clear, then maybe we can go for a band diagram now. So as I said, we have some bias, so now it will not be in equilibrium because we will have some different Fermi levels because we have different voltages at both ends. So I'm just making it like this, PN junction. So we have certain Na minus, and it is having a certain bias. I'm not marking it right now. I hope it is quite clear. So I'll again say I have certain positive voltage here and certain negative voltage here. So what it will do is, first of all, let me try to make uh, the conduction band profile, not the conduction, but let's say first make the Fermi only. Yeah. So what we will have, since we have a certain negative potential here and a positive potential, so the N side will get because we have a more voltage on the N side, so the Fermi level will be on the lower side. So I'll explain it a bit more. Let me try to make it first. And the Fermi level of the P side will be higher side. So let's say this is EFP. Yeah. So I'm making the EI now. This is EC, and let's say this is EV. So we have EFP and EFN now, two different Fermi levels. So this is what we call as quasi Fermi levels. So there is a topic in this particular week which is quasi Fermi levels. So if we have different Fermi levels for P and N side, that is what we call as quasi Fermi levels. So now you can see here very quickly that this is what we have as Q phi P from the previous problems, and this is what we have as Q phi N. And the difference in between these two is nothing but the applied reverse bias. So this is nothing but QVR. So now it is very clear that the VBI, sorry, will become equals to Q phi P plus QVR plus Q phi N. So this is what we have created due to the application of reverse bias. So VBI will be now on the higher side. That is, if I write, uh, so I have already written this. So we will have, let's say initially VBI old was VBI only, or the V total that we had. Let's say I'm writing it as V total old. So now the V total new will become VBI, and this plus additional reverse bias, that is VR. So this is the main difference. And if I write some theory to make you understand is, so if we apply a potential between the PN junction, so what we have is we will not, no longer we will be in equilibrium on applying bias. Let's say we'll no longer be in equilibrium. That is, Fermi level will not be constant. This is the first point to notice for any applied PN junction. So the second point is, as a positive potential is downward, the Fermi level on the N side, so EFN, is below the Fermi level on the P side, that is EFP. So we have already seen that the EFN is below the Fermi level from the P side, and the difference between these two will be nothing but the equals to the applied reverse bias voltage, that is VR. So that is why I have written the V total as VBI plus VR. And if I talk in terms of electric field now, so electric field in the neutral PN junction will be zero. We all know that in these areas, the electric field will always be zero. Electric field in neutral junctions or neutral regions is zero, or very small, you can say. That is what I meant to say, that the electric field, we all know that it originates from the positive to the negative side. And since we have a higher potential, so we will have a higher peak electric field for the reverse bias PN junction. I hope this is quite straightforward. So what I'm trying to say is, since we have a higher electric field, sorry, that is what we are confirming, that we have a higher depletion width. So that is why I told you in the initial state that once we have a reverse bias, we will have a more depletion width as compared to when we have no bias. So in very simple terms, the formula that we had for the total depletion width before, that is 2 epsilon s by q VBI, this is what we already had before. Sorry. I hope you already remember this. So the only difference will be this additional term plus VR. And similarly for the xn, we will have the same formula, 2 epsilon s by q. So we had VBI before, so there will be addition of the depletion width and rest remains same, 1 by Na plus Nd, whatever it was. So for n, Na comes above. And similarly for Xp, we will have Nd by Na. And I hope this is clear now. Is it clear? We will have an increased depletion width, and we will have the depletion width increase on both the sides. We will have a higher electric field, and the applied voltage now becomes the total voltage now becomes the built-in potential basically plus the applied reverse bias voltage. So this is what we have for a reverse bias PN junction. Is it clear to everyone? Any doubts here?
So why do we say upon applying an electric field, it's no longer in equilibrium?
Upon
Because my
yeah,
intuition tells me that the moment we apply an electric field, there might be some dramatic changes, but later on it will come to equilibrium, right?
okay. So first of all, we are applying the potential, not electric field. So since we are applying the external potential, so as I said that in the neutral region, okay, that is a good question. So in the neutral region, we know that the electric field will be zero. If I try to plot maybe very quickly, I hope you understand what I'm trying to do. So we have a neutral or a very small electric field in the neutral regions. So once I apply a certain potential, we will have a certain negative potential already existing here, and we will have a certain positive potential already existing here. So we need to have a higher electric field in between, and for having a higher electric field, we need to have a higher depletion width. First of all, do you understand this?
Yes.
Yeah, so once we need to have a higher electric field, and we know that we will have more diffusion of carriers on the p side, so we will have need to have a higher Fermi level on the p side, and we'll have a more electrons means closer to the conduction band, so it will go below and it will be more closer to the uh, what to say, it will go away, sorry, yeah, so we will have a positive potential. So what happens, positive means holes, so more holes means it will go very or away from the conduction band, you can say. So that is why it goes up and it goes down, because more the negative potential, more the Fermi level will go down, and more the positive potential, sorry, the Fermi level will go up, and more the positive potential, the more the Fermi level will go down. So this is how we reach to that. If we have a certain Fermi here, it should be below this Fermi level. So there should be a difference of the applied potential. We need to have a certain difference. Otherwise, if we have a same Fermi potential, that will ultimately mean that we have not applied any potential. So to compensate this, we should have different Fermi potentials. Maybe you can write that the VBI at this side will be, as we were writing earlier, it is as Q phi n plus Q phi p. But now we have an additional potential that is plus QVR. So to compensate this, one Fermi level will go up and one Fermi level will go down. And how it goes, I have already explained that more the negative potential it will go up, and more the positive potential it will go down. And that is the case we have in the Venn diagram also. Does it make sense?
Yes, sir.
Okay. Let's try to do a problem now. Okay, so now we are doing it for a forward bias. I hope you will understand it very easily. It will go the opposite way as we are doing for the reverse bias. So we have a forward PN junction. So forward means that the positive side is attached to the P side and the negative side is attached to the N side. So you need to choose the correct band diagram. Maybe you can take 2 minutes and let me know what is your best guess. Each and everyone, you can take 2-3 minutes and let me know what is your answers.
Sir, I think A will be the answer.
Which option you are saying? Could you please say it again?
A will be the answer, I think.
You're saying A.
Yes, sir.
Okay, so I'll wait for one or
Sir, B.
okay, so I've got one as B. Anyone else? Anyone else? Give it a try. And this is very easy if you understood how we make it for a PN junction for a reverse biased. It's almost similar. Okay, so let me try to explain now. So if you understood that the V total when we applied the reverse bias was nothing but Q phi n plus Q phi p, and we have got some additional reverse bias potential. So the same will go reverse for a forward bias. So what will happen? See, I'm here. Trying to explain mathematically first. So what will happen? This Fermi level difference will get lowered because once you apply a positive potential, the what will happen? There will be a reduction in the depletion width. So let's say this was a initial depletion width, and once you apply a positive potential, so what will happen? This electrons from the n side, there will be a more diffusion here, and due to a negative potential on the n side, these holes will there will be a larger diffusion here. So what it will do it will reduce the depletion width. So once the depletion width will reduce, there will be a reduction in the electric field also. So now, as I told you in the previous example, so first of all, let me eliminate option A and option C. Because we have certain applied potential, the Fermi level cannot be constant. So A and C can never will be the answer. I hope you already understand this, that Fermi level will only be constant for the cases in which there will be equilibrium. So in this case, we have applied a certain voltage, so there will be some uh, quasi Fermi levels that will be drawn. And now if I talk about option B and D, so in option B, you can clearly see that we have certain, maybe I can use some other ring. So we have certain Q phi P and we have certain Q phi N. And there is some overlap you can clearly see if I try to draw this. And this is QVA. I hope it is visible. Maybe I can zoom this, which will make the V total of Q phi P plus Q phi N minus QVA. And that is what is shown is in electron volts here. And for this case, option D, we have this Q phi N, we have this Q phi P, and the difference between these is very large, which is Q phi, oh sorry, so let's say QVA. So as I told you in the previous question that more the positive bias, it will move away from the conduction band, more the negative bias, it will move uh, away from the valence band or closer to the, you can say, negative bias will have a higher potential basically. So negative bias will have a higher potential. So it is true for both the cases, but you can see the difference in this and this. So for the reverse bias, we will have a higher total voltage, which was plus VR, and for the forward bias, we'll have a lower voltage. So the difference will be lesser for a positive forward bias PN junction. So option B will be correct for this case. I hope you get this. This is quite straightforward that the difference between the EFP and EFN will be lower for a forward bias PN junction as compared to a reverse bias PN junction. So that makes option B as the correct option. Does it make sense to everyone?
Sir, why not option D?
Yeah, option D. Yeah. So that is what I'm saying, that you can see that we have a VVI which is quite on the higher side for this particular option, because what it has done is the EFP, yes, it has moved quite below, and EFN has moved quite closer to the conduction band, but it it is not a possibility that the VA value should be greater than phi p plus phi n, because if I sum these two and like reduce these two, sorry, if I do the phi p plus phi n and then do the minus VA, so it will make it this as negative, which is not true because we have applied a forward bias. But if you do it here, you will get certain V total which is positive. You can clearly see that. Well, it might be possible that you cannot clearly see, but you can see that if I add these two things, one is this and one is this, and if I subtract it from these this particular small line, so it will be positive, right? And if you do the same for this case, VA will come out to be negative for sure. So this will, you can say that this is for reverse bias and this is for forward bias. Is it clear?
Yes, sir.
Yeah.
Okay, sir.
So option B will be correct for this particular case. So now since you know that what will happen to the depletion width and the barrier, so let me know what do you think will be the answer, that for a forward bias P injection, what will happen to the barrier and why it will happen. You can take 2-3 minutes and let's say this is option A, B, C, D, E. You can let me know your answers maybe by opening your mic or in the chat box. You can take 2 minutes to think. So I've got one answer as C. So let's wait for some more answers and then I'll discuss. Okay, so let me discuss if I'm not getting more answers. So first of all, it is talking about a forward bias free injection. What we have understood till now, that the Fermi level of the P side will be lower than Fermi level of N side. So this is the case for each and every bias P injection. And what will happen, that barrier will be reduced first of all, that we have already covered in the previous question. So the barrier will be reduced for sure. So option B will not be correct and E will not be correct. So we are left with A, C, and D. So barrier will reduce across the junction proportional to the applied voltages. That is true, but what it will do? So as I have said that once we have a positive bias, what happens is we have a positive voltage here and we have a negative voltage here. So what it will do, it will, as I said that we have a positive voltage here, so the electrons from the inside will go quickly towards the positive applied voltage and the holes from p side will go towards the negative applied voltage. So holes are the majority carriers, so the diffusion of majority carrier will increase towards the negative voltage, and here the majority carriers are electron, so the diffusion of the majority carriers will increase towards the positive voltage. So what will is happening is basically the diffusion is written where, yeah, so the diffusion of majority carriers across the barrier, so what will happen, the barrier will reduce because the diffusion of the majority carriers across the barrier. Does it make sense? Option C will be correct here. There is no diffusion of minority carriers happening because positive voltage is on this side, so majority carriers are having the diffusion. I hope this is clear that for n type majority carriers will be electron and for p type it will be holes. So the diffusion of majority carriers is happening across the barrier, which is basically resulting in reduction of the barrier. Does it make sense? Is it fine? So option C will be the correct answer to this particular question. Is it fine? Okay, fine. So let's move forward. Okay, so we have a question for a PN junction. Yeah, so this is now a question I've already told you, I guess, all the formulas. So we have a PN junction given in which we have applied reverse bias voltage of 5 volts. We have been given NA, ND, NI, KT by Q, everything. So we need to calculate that V total, the total potential across the PN junction. I hope you already know the formula now. So can anyone tell what will be the total voltage? Quickly. We have done it, the derivation also basically using the band diagram initially. So what will be the V total? Can anyone tell?
VBI plus VR.
Yes, exactly. So you can quickly let me know the answer for this problem. You can take 2-3 minutes and let me know what is the answer. This I've got one answer as 5.796. So I'll wait for maybe one more answer and then I'll solve it. This is very straightforward, I guess. You don't even need to solve it after uh, seeing all the options. So let me do it. So first of all, since VR is 5 and VBI will be something positive, so the V total should be greater than 5. So that is only one option, which is 5.79. So you don't even need to solve it in the initial thing, but we can solve it. So VBI will be, sorry, VT NAND by NI square for the PN junction. So you can go for 0.026 ln, what is NAND? So this 2 times 17 and 16 is 33 and NI square is 1020. So this will come out to be around 0.796 volts and the V total will be nothing but 5 plus 0.796, which is 5.796 volts. So option C will be the correct answer. So I hope it is clear. This was very straightforward. So for this same question, you need to calculate the ratio of the depletion width with and without the applied reverse bias. I hope you understand the question. Do you understand this question? Please let me know if you understand the question.
Yes, sir.
Fine then.
It will be degrees, sir.
So the upper thing is when the voltage is applied, that is, and the lower is when the voltage is not applied. So you need to find the ratio. This is again very straightforward. Maybe you can take 2 minutes and let me know your answers in the chat box. Any answers? I'll wait for 1 or 2 minutes more then. This is very easy. Okay, so what one answer is 2.69, 2.7 basically. Anyone else? Anyone else with some answer? Okay, so let me try to solve it. So we all know that the depletion width formula, as I already told you. So if you are not applying anything, this is 2 epsilon s by q. This was VBI plus VR, and this is nothing but 1 by NA plus 1 by ND. So can I say that when it is V is equals to VR, so this will be, if I divide it by W when V is equals to 0. So all of these terms which I am marking in red will get cancelled out on division, and what we are left with is VBI plus VR and divided by VBI, because for the lower case VR is 0. And VBI we already calculated in the previous part, which is, what was VBI? 0.79, let's say. 0.79 plus VR is 5 upon 0.79. So this will give you around 5.7 divided by 0.79 under root. And I guess this will come around 2.7 only. So option D is correct answer. Uh, is it clear to everyone?
Yes, sir.
Yeah, so let's go ahead then. So now we have a new question, which is the built-in potential for a abrupt PN junction again is 0.75. So VBI is given as 0.75. the junction capacitance. So junction capacitance is nothing but epsilon A by D. I hope you know the capacitance, very basic capacitance formula. So what it comes in, we know that the depletion width, we already have the formula which I have written here. So this is the depletion width W. So if I say that the junction capacitance is inversely proportional to W, and this is the case for an abrupt p-n junction only, because we have calculated the W for abrupt p-n junction there. So what I can say is 1 by W, so I can write this as 1 by VBI plus VR. Does it make sense to each and everyone? Any doubts here?
No, sir, clear.
Please repeat again, sir.
Okay, I'll repeat. So what I can say is the junction capacitance is inversely proportional to the depletion width. This is very basic thing, epsilon A by D or epsilon by width only. So it is inversely proportional to the width. And in the previous question, I have just told you that the W is dependent upon this VBI plus VR. So here I can write this W is proportional upon VBI plus VR. So this is what I have written, that this is proportional upon VBI plus VR. So this is what I have written. Is it clear?
Okay, sir.
Yeah. So now the question says that the built-in potential is given. Okay, so I've already got one answer as 0.5. So let's check. So if the junction potential at reverse bias VR, so at VR equals to 1.25, we know that Cj is given by 5 picofarad. So now the question is asking that at VR equals to 7.25, Cj is what? In picofarad only. So this is what you need to calculate. So this is quite straightforward. Maybe you can take 2-3 minutes and let me know what is the answer. So I've got one answer as 0.5, I guess. So we'll check it in 2-3 minutes. So let's try it. All of you can try to solve it, and we'll solve it in 2-3 minutes. Uh, please share your answer on the chat box as quick as you can. And I guess Vani has given the answer. So maybe Vani, you can also recheck your calculations.
Okay, sir.
Okay, so I've got one answer is 2.5 now. So I'll wait for one more answer from anyone else and then I'll solve it. Uh, please try to solve anyone else if they can. I'll give you 2 more minutes. This is simple mathematical calculation. Anyone else? Okay, so I've got one more is 2.5. Okay, so let me try to solve it now. Yeah. So what I am writing, I am denoting one as CJ1 and one as CJ2. So then this is inversely proportional. So I'll write this as VBI plus VR1 and this is VBI plus VR2. So at VR1, CJ1 is 5. So I'll write VBI is, what was VBI? 0.75 plus what was VR1? 1.25. And this is 0.75 plus, and what they are asking it as 7.25. So we need to find CJ2 now. So 5 by CJ2 will be, so this will be under root 8 divided by under root 2. This will give me under root 4 and this will be nothing but 2. So CJ2 will be nothing but 5 by 2, that is 2.5 picofarad. So yeah, 2.5 will be the correct answer, which is option B here. Does it make sense to everyone? Any doubts here? If you have any doubts, you can ask straight away. So you can relate here that for a higher reverse bias voltage, we have a higher depletion width and we have a smaller junction capacitance. That is what we should get. So let's move forward now. So now we have some similar problems, or maybe the week 5 assignment problems. I guess this was also given in this week's assignment problem. So we'll move ahead now. So now the question says that the capacitance of PN junction diode, and we have four options. One is decreases with the increase in the forward bias voltage. Then we have increases exponentially with the increase in the forward bias voltage. Then we have increases linearly with the increase in the forward bias voltage. And the last option, it does not change with the increase in forward bias voltage. So we need to check whether what is the role of junction capacitance, or what is the change in the junction capacitance with respect to the forward bias voltage. If it increases, what happens? If it decreases, what happens? So maybe you can choose the most apt answer and let me know in the chat box. Let's say this is A, B, C, D. So already got one answer as B. Anyone else? You can take 2 more minutes quickly and then we'll maybe go through all the options.
Option A, sir.
Okay, so I've got one answer as A, one answer as B. I guess two answers as A.
Sorry, sir. A not. A not.
Sorry, are you? A is not your answer, you are saying.
Yes, sir.
Okay, so what is your answer then? Okay, I've got one another as A. So two votes to A and I guess two votes to B. Anyone else? Okay, so let's discuss and all the options. So since most of you are saying A, so let's discuss A first. So it says that the capacitance will decrease if we increase the forward bias voltage. So first of all, we have, let's say, a W, which is something like this. So I'm writing So for reverse bias, it was VBI plus VR. So forward bias, what it will be? It will be nothing but VBI minus VA. And this will be same. I hope everyone understands this. This is nothing but the forward bias and this is nothing but the reverse bias. So more the reverse bias, more will be the W. That is what we heard, that more will be the forward bias, lesser will be the W, right? Does it make sense to everyone?
Okay, sir.
Yeah. So forward higher forward bias voltage means we have a lesser W and that means we will have a higher capacitance because C is nothing but epsilon by W. So it says it decreases with the increase in forward bias. So A cannot be the answer. Those who all are saying that A is the answer, I want to correct them. I hope you. I hope it is clear that A is not the answer, right? Does it make sense that once we have a PN junction and if we apply a forward bias, as we see that forward bias, we will have a steeper depletion width and lesser W means higher capacitance, right? Please confirm if you are able to understand this.
Understood, sir.
Yeah. So A cannot be the answer. Maybe we can move forward then. So it says on increasing the forward bias, it increases exponentially. So let's keep this option in check. Exponentially means as some power. So what it is happening here is, so we have a W. If we are increasing the, let's say the forward bias, we are having a decrease in the, so I'll write this directly. So if we are increasing this, we are having a reduction in this and we are having an increase in this. So you can see that it is not increasing linearly. First of all, it is increasing at some power. So maybe I can write maybe something like VBI minus VA raised to power minus 1 by 2. This is what I can write basically. So on increasing VA, there is a reduction in what was that? There is an increase in CG. Sorry, and it is not quite linear and this is some power dependence. So for power dependence we can say that it is exponential only. So we need to consider option B can be correct, but let's see what are the more options. So the third option says that the capacitance increases linearly with the increase in the forward. So linear is not surely the not the correct answer because we have some power dependence. So again option C cannot be correct, A cannot be correct, and it does not change. So this is again not correct. So since we have some power dependence, so the most apt answer for this particular question will be option B. Does it make sense to everyone? Because this can be a tricky question. Does it make sense? First of all, we are sure that if we increase the forward bias, we will have a higher capacitance. So answer would be either B or C. So C cannot be the answer because it is not increasing linearly because we have some power dependence. And it does not even say that what kind of p-n junction we are using. So let me give you some more information that for abroad p-n junction, the Cj is dependent upon 1 upon under root Vbi plus Vr or Vbi minus Va you can write. And for, I guess there are one more case that has been taught in the theory, that is for linearly graded p-n junctions. I guess it is already taught. What we have is Cj is proportional to Vbi plus Vr or Vbi minus Va to the power 1 by 3. So in total, what we write in general is Cj is directly proportional to Vbi plus Vr raised to power minus m. M is equals to 1 by 2 for abrupt p-n junction and m is equals to 1 by 3 for linearly graded p-n junctions. There is a whole derivation associated to it. You can look if you want to go deep into this. Is it clear to everyone? Shall we move ahead? Any doubts in this?
So in this formula, if it's forward bias, VR would be replaced by minus VA, right?
Yeah, 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 yeah. So it will be something like this: VB minus VA.
Okay, sir.
Yeah. So let's go ahead then. So this is a very straightforward question. So it says we have a silicon bar which has doped with ND only. So we have an N-type silicon bar, something like this. We have Ni given as 1.5 times 10 is per 10, and the complete impurity ionization has happened. So at equilibrium, the electron and hole concentration is what? So N naught and P naught it is asking. So this is very straightforward. Maybe you can give it a go. At max, you can take 1 minute and let me know what is the answer. Are you trying it? Please confirm if you are trying it. Otherwise, I'll solve. So I've already got C as one of the answers. I'll wait for one more answer and then I'll also solve it. So I've got two answers. One is A. Anyone else with some different answer? Okay, one more as D. Okay. I've got three options now. One is A, one is C, one is D. B is left. Anyone wants to say B? Okay, so let me try to solve it. This is very easy. Okay, so we have a silicon bar which is doped with ND. That means it is a N-type silicon bar. Everyone agrees with this? Everyone agrees?
Yes, sir.
So if we have
Yes,
an
sir.
N-type silicon bar, we know that N at equilibrium will always be equal to the ND, and P at equilibrium will be calculated by N naught. P naught will is always equals to Ni square. So P naught will be nothing but Ni square by N naught, that is Ni square by Nd. Does it make sense? Does it make sense to everyone?
Yes, sir.
So clearly option A and B cannot be the answers. It will either be C or D. So N naught will be directly Nd, that is given as 2.25 times 10 is power 15. And we can easily calculate P naught, which will be Ni square. That will be, I guess, Ni square is 2.25 times 10 is power 20 divided by 2.25 times 10 is power 15. So that will come out to be approximately 10 raised per 5 per centimeter cube. A moment. So option, okay. Did I do some calculation mistake or what? Mm-mm. This is 20. I need to recheck the options, I guess. Can someone confirm if I've done some calculation mistake here?
No, sir.
No, sir.
Options.
Calculation options are wrong, I think so. We tried many times, sir, by substituting different formulas.
Okay, okay. So you are saying all the options given in the questions are wrong.
Not all, sir, but for C answer is correct. It's 10 power 5 only, but we are getting the 10 power 10.
Okay, okay. So this should be
It's
5.
5.
Yeah, yeah. So I guess you should talk to the NPTEL, I guess, in the discussion
Yes,
forum.
sir. Yes, sir.
So yeah, most probably it will be 5 if I'm not wrong.
5 only, sir.
Yeah, so maybe you can talk. So any option is not correct in this question as of now, but I guess it should be 10 is per 5 only. Okay, so we can move forward then. So this is more of a theoretical or a derivational concept that for every 10-degree increase in the temperature, the reverse saturation current will increase by 2 times. I guess this derivation is already taught in the theoretical lectures, right? This is a quite a long derivation, so I'm not going through, but you can write that the reverse saturation current at T2 is nothing but the reverse saturation current at T1 times 2 raised to power T2 minus T1 by 10. So if T2 minus T1, the change in the temperature is 10, then the reverse saturation current becomes twice of the previous current. I hope you have already gone through all of these derivations of diode, etc. Because the last topic of this lecture is the ideal p-n junction diode equation. Are you all aware of the diode equations? So maybe I can give it a very quick overview. So we in the diode we know that the total current is nothing but the reverse saturation current multiplied by the applied voltage by Vt minus 1. So this is the ideal diode equation where Is is nothing but Q dp Pn naught. So Pn naught will be maybe, give me a moment. Uh, 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 yeah, so it will be, I'm writing in the direct formula not in terms of Pn naught. So Is will be AQNI square dp by Lp plus dn by ln Na. So this is this Is and this is the ideal diode equation. So this is the last topic and we already know that what is Ni and all. Do I need to do the derivation or you are already aware of this? Please let me know quickly.
We are
Because
aware of it, sir.
yeah, so if you are aware, then most of the problem I guess in this particular week are dependent upon direct these two formulas only. So let's go into the problems only. So this was quite straightforward that for every 10-degree increase we have a 2 times increase in the reverse saturation current. There is a whole derivation associated, you can check it out in the theoretical lectures. So let's move forward now. So we have again a p-n junction diode in which Na is given, Nd is given, Ni is given, dp, dn, tau p, tau n, epsilon r, everything is given, and you need to calculate. The first part is you need to calculate the ideal reverse saturation current. So I have already given out the formula. You have everything, I guess, in this. Just try to calculate it and let me know what is the answer that you are getting. Okay, so already I have the answer. One answer is D. So I'll give you 2 more minutes to solve each and every one, and then we'll confirm if the answer is D or not. Okay. Okay, so one more thing to add is we need to calculate the current density. So we don't require this area. So we need to calculate Is by A, that is Js. So forget about the area. Rest all the terms remains the same. So I've got one answer is D. I guess two answers now is D. So let me also quickly try to calculate it. Yeah. So it is nothing but A will go away, Q Ni square by dP by Lp Nd plus dN by Ln Na. I hope I've written it correctly. Yeah. So we have Q and Ni, everything given. So this is 1.6, 10 raised to the minus 19. Ni square will be 2.25, 10 raised to the 20. Then the whole bracket. Okay, so we need to calculate Lp, which will be nothing but under root dp and tau p. So Lp will be dp is what 25 and tp is what 5 raised to what sorry 5 10 minus 7. So this is in centimeters. Yeah. So this is something 125 10 raised to the minus 7 centimeters. That will be under root 0.125 to 10 raised to the minus 2 centimeters. Similarly, Ln will be, what is Ln now? Ln is 10. Okay. 10 into 5, 10 is per minus 7. So it will be 50 and 50 is 0.05, 10 is per minus 2 centimeter. So we'll just keep each and every value. This is 25 by whatever I'm getting, 10 is per minus 2 centimeter, and ND is what 16. So ND and NA I'm like dividing outside because both are equal, plus 10 by under root 0.05, 10 is per minus 2. So this is what we'll get. It's all about calculation. I hope you'll be able to solve it. I'm not sure if D will be the answer, but I hope you got the concept right. So if I'm not correct, this is, if I'm correct, maybe this is 10. This 10 is per 4. What else we are left with? 4. I mean, you need to check what exactly will be the answer. Mm, yeah. So you need to check what will be the answer. The calculations will be like this only. Is it fine? Shall I leave it? Okay, then we can move ahead. Okay, so we have this. So if the depletion region width, so if the W increases from 150 nanometer to 300 nanometer due to increase in reverse bias voltage, what factor does the junction capacitance change? So first of all, if W increases from 150 to 300, so will the junction capacitance increase or decrease?
Yes, sir.
Decreases.
Yeah, it will decrease because we have a higher W. So answer cannot be C and D because they have a higher value. So just try to calculate it. This is quite straightforward, I guess. Let me know the answer in 1 minute. Okay, so I have already got 0.5. Anyone else? Okay, so 0.5. So we know that it is inversely proportional to W. So Cj1 by Cj2 is W1 by W2. So let's say it was Cj1 earlier. And for Cj1, what I have is W1 was before 150 and it was 300 later. So Cj2, sorry. So I'll need to write it again. I guess it got vanished. C Cj1 by Cj2 is W2 by W1. So Cj2 becomes 1 by 2 of Cj1. So that is what we need to calculate. So the change is Cj2 by Cj1 and it is changing by half. So option B will be correct. Is it fine with everyone? I guess this was a very straightforward question. So yeah, is it fine? Everyone?
Yes,
Okay,
sir.
sir.
Okay, fine. So I guess we have covered most of the topics that are given in the course outline. And one more thing I would like to discuss is, since I've seen that there is a clash in the session for Tuesday, that we have one session from 6 to 8 and one from 8 to, I guess, sorry, 7 to 9, I guess. So what I'm thinking is to prepone this session every Tuesday from 5 to 7. So is it fine with everyone? So instead of having this session from 6 to 8, we'll have it on 5 to 7 so that it will not clash with other session. Does it make sense? Shall we do it?
Yes, sir.
Okay, so maybe in the group also you can announce that we can have sessions from 5 to 7 on NPTEL will also let you know. So I'll talk to the management and maybe try to reschedule the session from next Tuesday itself. And one more thing that I like to announce is for week 6 and 7, I'll take the session together. I mean, I guess for the next Tuesday, I'll take the session for week 6, maybe from 5 to 7 itself. And on that same week only, the next day, I'll take the session for week 7 from 5 to 7 again because I'm not available on 10th of September due to some work. So I guess on Tuesday, next Tuesday, I guess it is on 3 September. So I'll take two sessions. One is on 3 September and one is on 4 September. That will cover week 6 and week 7. So I hope you'll try to join the same. I'll put the reminder on group also. So it will be from 5 to 7 p.m. You will have a announcement if it is from 5 to 7 p.m. Otherwise, it will again take place from 6 to 8 only. That is fine.
Yes, sir.
Sir.
Okay, fine. So if you don't have any doubts, then we can dismiss this session and we'll meet again same time or from 5 to 7 on next Tuesday. So thank you everyone for joining. If you have any doubts, you can ask right now. Otherwise, we'll close the session. Any doubts?